Hi, everyone. My name's Anusha. I'm going to be presenting on a topic that I've been recently getting more involved in and also passionate about. And they're going to be talking about probabilistic programming for recommender systems. Recommender systems, I'm sure, as you know, are, kind of in almost every single domain, like let it be e-commerce. I'm currently working as a data analyst at a publishing company. So we use a lot of recommender systems in our work when it comes to recommending maybe similar articles that you might be looking for that might be relevant to what you might be doing, or just other things which I'll dive more deep into. So this is a topic that I grew interested in when I was finishing up my master's fairly recently at Columbia. So there's a lot of faculty and work that's being done there, especially in the space of Bayesian stats and also like a lot of applied machine learning. Yeah, I'll go ahead and get started. So how today's tutorial will work is I've got some slides just to contextualize for those of you who might not know about recommender systems and the stats behind it. And then I've got my code up here too. I made a little bit of changes and updates to it. I didn't update it onto the GitHub yet, but hopefully I'll do so after today. But yeah, you're more than welcome to follow along with that. It's okay if you don't want to, but that's just there for reference. So I'm just going to be going back and forth with both the tabs. So yeah, we'll go ahead and get started then. So I was kind of already getting into what recommender systems are. So they're kind of grouped into three buckets. You've got collaborative filtering, which is what we're going to be focusing primarily on today, which is this focusing more on users, like what their preferences might be, like how are they rating, liking, disliking objects, or other items, and then filtering, also still filtering recommendations. You also have content-based filtering. So this is like very metadata based, based on your specific item that the user is engaging with. This might be a song, like looking at the genre, artist. Maybe it might do something with e-commerce. Might be taking a look at specific products, maybe like what section that they're grouped in. I mentioned my industry, publishing. It might be dependent on like, what journal the article might come from, and maybe language the article is written from, things like that. And then you have this modality where you're able to combine both users and items, which we'll take a look at a little bit today. But it still focuses more on the collaborative side of things. So that's what the hybrid recommender system is. And then these are just some examples on where you might run into recommender systems each day. So I mentioned shopping, movies. The data set that I have on the notebook today is a movie data set. So yeah, feel free to take a look at that. I picked that data set in particular because it's a lot cleaner data. Modern day recommender systems data, that especially the ones that I've worked with, also have text data. So that takes a little bit more time to pre-process and, vectorize, turn them into embeddings. So it requires a little bit of work there. You have like even reviews for restaurant data. I know Yelp is also like another common database where, you might be looking at, oh, is this restaurant worth going to? Or what are some other similar restaurants based on my preferences when it comes to the cuisine or maybe how it's made, things like that. And then, those are just some examples. There are challenges, unfortunately, with a lot of problems that we deal with day to day. So these are some of the common problems that recommender systems face. So one instance is a cold start problem. So this is when you have new users entering in the system, right? Like in today's world of data science or just like even with AI, like you're going to be having new data and databases being very ever changing, and a lot of things could be happening. So you have a new user or item enter the system, and you might not necessarily know what sort of preferences they might have, or what sort of items that they like or engage with, who the user is. A lot of unknown information. So with the baseline recommender system, which I'll show you in a little bit, like trying to explain what it will show and also why it's very limited in that it doesn't take into consideration of a lot of different latent factors describing the user. You also have problems with sparse data. So maybe there are certain users that are not ranking the data enough, which is what you'll see with the movie data set. You might have some users like giving less than 20 reviews, for instance. So I'll show some examples there as well. And then you might have instances where, yeah, you'll get overconfident predictions. One code example that I have here is ratings are between 1 to 5, and then sometimes the recommender system might give above or below that range at times, and then say that, yeah, I think a review user would give this a 5.5, even though it's not within bounds, even though maybe internally they might be thinking that way, but we don't really know. So I'm just gonna go, if you have the notebook, you can. Okay, yeah, if you have the notebook, feel free to follow along. But yeah, I just have some of the packages here, and then this is the data set. You can check if you can, like, when you load in the data set, feel free to take a look at it, just to see, what are the variables. So you have user ID, item ID, which in this case would be the specific movie, the rating that the user gave it, and then timestamp. But we're not going to really be focusing on the timestamp. There's a lot of extensions you can do with that, but yeah, I won't get into that today. And then, yeah, I split them into training and test sets. And then I wanted to make the case as to, why I'm emphasizing sparsity, because you've got 943 users, but 1682 items, and you've got 100,000 ratings, but that's only like 6.3%. So you have a lot of empty, let me just show here. Yeah, so you have all this white space, which we're, trying to make sense of. With different users and different items as well. And then, when you have new movies or users entering in the system, like, where they might fit in this whole rating matrix. So yeah, I just wanted to visualize that and put into context as to, why this is important and why I'm bringing in that probabilistic framework to help. Yes.
Sorry, what was the website that we could find this notebook on?
Oh, it was shared yesterday. It was the GitHub link under the session name. I don't know whether it's like didn't
Okay.
come up.
I probably wasn't there for it. Continue, sorry.
Okay, they sent the program. It
Okay.
came through email. Yeah.
Oh, okay.
Yeah. So sorry. Some of these, yeah, like I mentioned before, some of these were added recently. So I know the notebook that you all have access to might not be up to date, but for the most part it is. So yeah. Did anyone else have any questions? Yeah, feel free to stop me if anything comes up or
I don't know, maybe it's irrelevant, but I know that for sparse data, you usually sometimes use lasso optimization. Is it something that you also use?
yeah. Actually, in this case, I think I focused more on, yeah, I would say lasso in this case, because you might have a user that might have not given as much, they weren't as engaged giving much reviews. So that's where that penalty will like completely, or you can use a ridge to like, reduce their effect. But yeah, that's very common in this case. But then in the probabilistic framework, we have like, we introduce different priors and a whole different structure to make sure that like every user is counted. Whereas, yeah, when you introduce some of those penalization metrics, yeah, it might like totally take them out of the picture. Okay, yeah. Again, feel free to stop me if anything comes up. Yeah, I mean, this would be great, like if this is something that you're working with on a day-to-day. So I'd love to hear even some of the experiences that you've encountered with methods-wise, application-wise. Yeah, we'll try to keep this discussion as well. And then let me see, I can talk kind of about the overconfidence. Okay, yeah, maybe I'll talk a little bit about that. So I did a sample baseline recommender systems. So yeah, with the training data, didn't apply it to the test data quite yet. So first trained my model on the recommender system. And then, yeah, wanted to take a look at specifically of users who left less than 20 ratings. What their average, or not what their average is, but yeah, just to get a count of how many users that we've on total have left fewer ratings. And then we wanted to take a look at someone who has like over 150 rating counts, and then a sparse user who doesn't have that much. So you can see here already someone that has like 208 ratings, their prediction is 4.53 for movies, whereas user B says 12 ratings and their prediction is 5.51, which is like way above the bound. So you'll see some of the limitations with the recommender systems is, yeah, one is the latent factors. Like we don't know whether if the user is, maybe they have a preference towards a genre or director. There's all these different complexities, especially, you know, when we factor in human decision making as to, you know, why they might be rating certain things a certain way. And then, yeah, also keeping it within the bounds too. So yeah, this kind of gets me to my point right here. So this is how I built the baseline recommender system. So I'll talk a little bit about that process if you're interested in trying it out, especially for another data set. Yeah, like I said, just for simplicity's sake, I focused on the movie lens data set because didn't have to clean the data out as much. So yeah, we have the columns, read the data set, train and test. So put the test set as 20%. And then, yeah, also factor in the user item bias. So the global mean is the training data sets average rating for the whole training set. And then the user bias is you're grouping by the user ID with the rating and you're getting a mean from that. And you're going to take the difference from the global mean. And then the item bias is the specific item ID with the rating, that mean, and you're going to subtract it from the global mean. So the function that I write here, basically what the recommender system is built off on is the global mean, which is the training data set's rating, plus the user bias using the user ID. And then we'll add it with the item ID bias. So that's how the recommender system is defined here. And then we apply it to our test data set to get a prediction. And then I'll go over the different metrics that you can use to evaluate your recommender system, but we'll stick with the root mean squared error for now. Usually you use RMSE or the MAE that gives a sense of how well your model is doing in terms of recommender systems performance. So yeah, we call it the baseline RMSE. So yeah, you can just calculate that formula with the test data sets rating and then the predictions that it gets, and then it takes the difference and then square roots it. And then yeah, the baseline is 0.9633, which that means like the ratings are off by like, I'd say by approximately 1. And then yeah, that is, yeah, and then this is just like a sample that I was talking about. And then I just wanted to go back to the notebook really briefly and then just also show you to the rating distribution of the data set of the users. So like just looking at, because this will matter going into the probabilistic side of things, you know, when we decide to choose what we want as our mean, this will matter because we're trying to see, okay, are more users rating them lower on average or higher? So you can see that they're somewhere between 3 and 4, right? Yeah. So I think that's where like the mean median would sit ideally there. So I just wanted to show that. And then here are some of the different recommender systems metrics. So they're kind of grouped into 3 buckets. You have the predictive quality metrics, which is what I introduced earlier, which was RMSE and MAE. And then you also have ranking quality metrics. So that might be taking a look at, okay, how well the recommender system does when it comes to ranking different preferences that a user has. So yeah, that might be taking a look at precision at K. We also have, yeah, like NDCG, DCG, hit rate. And then you also have like behavioral metrics. So maybe like how diverse the recommendations are, how novel the recommendations are, any sources of bias, coverage, does it like capture, some of the criteria that the user is looking for. So these are some of the different metrics that recommender systems are grouped into. But today we're going to probably be focusing mainly on predictive quality. There's different models that do factor in some of the other metrics. So I wanted to briefly touch over some probabilistic programming concepts, and then we'll dive right into the notebook. So we'll continue the back and forth. So yeah, let me go ahead and show this. So for probability distributions, this is key because depending on what sort of data you might have, this is the different values that it could take. So there's different sorts of distributions. So today we'll be focusing on the normal distribution, and everything else depending on your data. Like binomial is usually yes, no, or 0, 1. That won't be really necessary in this case. And then you also have like exponential, geometric, hypergeometric. So yeah, this all kind of depends as to what exactly your data set is focusing on. So that's that.
That's a good question.
Yeah.
So this distribution is for the distribution of the 1, 2, 3, 4 up to 5, like how people rate it. But we see in the data set that it's not exactly symmetric, right? Like it's skewed a little bit towards 4.
Yeah. Yeah. So with this specific case, it's more as to like the data type. So for binomial, it might be like how many categories. Yeah.
But we have our data is in terms of 1 up to 5.
Yeah, 1 to 5 in our case. Yeah.
And this is the distribution of that corresponding to the, I don't know, rank. No, that's not rank. Quality of the movie.
Yeah. With the rating. Yeah.
And this we're going to use as our prior.
The priors will be like when I had showed the graph, right? Yeah, you'll probably decide like, okay, I have 3.5 on there, but maybe it's better to, you might think, let me go lower. I'll do 3.2 or 3, or maybe I'll go on the little higher side since there's a little bit more at 4. So yeah, it will be the mean based on the rating. So what you think it is, and then, when we run the likelihood, that will depend on what the data actually is. So yeah. Great. Okay. So yeah, that's just a little bit about the probability distribution. And then, to kind of a good segue into the next concept, which is on prior, likelihood, and posterior. So ideally with the posterior, you want something in between with what you believe in, which is the prior, and then the likelihood is taking the observed data that you have, and then you kind of want something to come up in the middle. So yeah, this is just a little bit of the formulation. So we've got the prior, which is the initial belief of the parameter. So in our movie example, it might be that, I think that the rating is 3.5, but then the likelihood might say, it's maybe a little bit more towards 4. And then posterior is like trying to combine that a little bit more. But there are instances in which, the posterior might reflect more of the prior because there might not be enough data, or vice versa. The posterior might reflect more of the likelihood because prior isn't really well defined, or there's not much information. So this will come in handy, especially when you have those issues with sparse data, or when you have a new user entering in the system. So yeah, those are some examples there. And then, okay, so I'll go back to the notebook then. See where we left off. Okay, so today's tutorial, I used the PyMC package. So you should be able to see that up here. I used to be using the PyMC3, but then that got discontinued. So in the notebook, there's also further links. So you're able to read the documentation a little bit more as to, what the model consists of. And then also, what are the different, like how you would go about defining your model. So this is just like a sample toy model that I made using the data set that we have. So You first would define what your model name is. So I called it toy model in this case. And then you would have your mu, which, I put as 3.5 as an example, but you can change that because then that will affect your other evaluation metrics that you're taking a look at, like RMSC or MAE. So that's also very dependent on that. You have sigma, which you need to define. So I use half normal so that I can avoid having any negative numbers, keeping it positive. And then ratings is what we're trying to be getting out from. So we have a normal distribution. We're using the ratings column of our data set, and then we have the mean sigma defined. And then, I'm taking the training data set, and then I'm keeping it small for this reason, because the more data you have, the more, time it takes to run. So I just kept it simple for now. You have the trace toy. So I defined the likelihood function. So that's trace toy. So in order for you to run the likelihood, you need to define, how many draws you want to do. So 500, and then the total is 700, but 200 of those are just, discarded to get the model to slowly start training. And then I just do it once. That's what the chain says. Return inference data, progress bar, random sequence. So that's all part of the model. So you can set that as to how you want.
Kind of goes back to the previous question, but is the choice of the normal just for ease of exposition here?
Yeah.
That discrete random variable like
Yeah.
values.
Yeah. No, yeah, because there's like potential extensions. You can do with that, but I wanted to keep it simple, so I stuck with normal. But yeah, there's definitely more you can do. So yeah, I just put that there on context that not everything in the actual world is normal. There is instances where it's like geometric, or you might need like the Poisson distribution. So that's where exponential would come under. Yeah. Sweet. Yeah. And then there's like various things you can do with this package, which is great. So you can do, I'm just plotting the posterior out here, and I'm plotting the mean. And unlike we have, I think in one of the earlier presentations today, they were talking about the credible interval. So yeah, that's what the 94% is, that the mean is going to be falling in between values of 3.3 or 3.7, and our mean falls right at 3.5. So yeah, again, this is just like a sample of how this works. So yeah, I'm gonna just take a pause because I felt like I went through a lot of content. Yeah.
Excuse me.
Yeah.
I'm fixated on the slight bump on the right side. Maybe I'm naive, but is there a reason that's there and it's not like a perfectly normal?
Yeah, that's true. No, that's a good question. I didn't think of it because I saw the mean being 3.5, and I'm like, all right. No, but that's a good point. Maybe there could be some other like one point that might be influencing it that way. So yeah.
So I'm still having a bit of trouble understanding normal to keep your values of sigma, or how exactly what's the value out of it.
Yeah, it like at least when I was reading about it, because even I was thinking that too, like, why can't we just keep it normal? Because with the data set that we're working with, it's just, positive values. So I think it's, just keeping it there. Because I was thinking too, like when we build the formula, like the initial formula where you have the bias, like maybe you could get a negative number from that, like, 1 point, like user or item bias might be higher, so that might drive something. So I was just thinking maybe in that case that it's just to avoid like a situation with that where you might have bias throwing off negative values. Because I would have maybe just stuck it as normal, but even with some of the work that I've done, but that data is a little bit different, so I'd stick with half normal. But something with a simpler data set, I think they were just like, okay, let's stick with half normal in this case. Yeah, no worries. Okay, sweet. Yeah, hopefully, you're able to, play with this on your computers, being able to run it as well. I'm doing this over Colab, so hopefully your environment has been friendly to you. So yeah, I guess I have a little bit more time. So I wanted to also talk about potentially another model as well, which is not on the Google Colab, the one that I've updated. So I just wanted to go over, there's a lot of different applications going on with probabilistic modeling in the recommender system space. So one common one is matrix factorization. So actually, when I was working on my thesis, I was doing some related work on some of this. So this is focusing more on the rating qualities. So the hierarchical modeling, which I'll talk a little bit about later, which will focus on like overall users and then each individual user. That's helpful to see in multiple stages and tiers. But you also, it's important to also take a look at the foundation, which is the matrix. So in this case, like I point a situation here, which is two users with identical average ratings might completely have opposite preferences, but then the bias model will treat them identically. That's the big issue because, they might give it same rating, but then their rating preferences are different that we can't really capture that with the baseline model. So matrix factorization fixes that. So we'll have user and movie represented as a vector in a k-dimensional latent space. So users will be the number of users. In our case, it's like 943 users. And then k is, depending on how you define that as. With the notebook that I had it as 10, but you can see that might be a bit too big with this model. So that is user's taste profile, and then n items is focusing maybe on the movie, and then the predictive rating is the dot product of the user vector and the movie vector. So it'll be u times v. And then, yeah, the k dimensions, you usually define that. There are ways to find the optimal number of k on how you want to define that as. So that's one instance to get k. So I have the Y Bayesian part. With a standard matrix factorization model, it will provide point estimates for U and V. The Bayesian version will place normal priors on both matrices. So just making sure that like each user is accounted for in the estimation. And then, because the issue that we've been having is that users that don't rate as much or movies that don't have much ratings, they will get penalized, which is what the earlier question was being asked about. So this model is more cautious and gives more uncertainty about users and items we know less about. So yeah, this is a way how to build the matrix out. So yeah, we do the same training, splitting it into training and testing, and then converting it into label encoders, and then so that it fits the model, and then you split it into a test sample, and then you do the same thing, and then if you want to see how many unique users and items you have, and then this is the factorization model. So we're bringing in the half normal hyper priors here. Let me just make sure this is the right. Yeah, this is the right one. I just wanted to make sure. And then you have the global mean, individual user, individual item. I'm going to get a little bit more into that in depth. And then we have U and V. So we have the user matrix and then the item matrix. And then we also have the dot product, which I've mentioned, and then what we're expecting. And then factoring in the observation likelihood, and then I have the likelihood here. So I got this error because unfortunately with the draws and then like the parameters, because we're doing 10 times, I think like 1900. So it was taking too long. So unfortunately I wasn't able to show that here, but this is an example of like, this is what like the matrix factorization ideally would be trying to solve problems like sparse data or cold start problems. So I just wanted to show that briefly. I know that wasn't the focus, but I found some extra information that, I thought I'd share. And then, with the matrix factorization, some metrics that you can use to evaluate your ratings would be maybe taking a look at precision at K, the NDCG as well. So yeah, those would all be some good instances. So yeah, let me go ahead and get into the focus of the hierarchical multi-level modeling. So that's what I focus primarily on today. So this setup is beneficial because you've got the whole user population, but then you've also got individual users to account for. So you've got the higher level. So here's if you want to apply it conceptually. So you've got the higher level, which, you might be taking a look at salespeople, and then individually are the customers, or, even a more simpler example, you've got schools. Below that, you've got teachers, and then you've got students. So you still want to overall evaluate school performance, but then you want to see in different levels, like how the teachers might be performing. Are they contributing to the school's success or failures? Same thing with the students, how they might be playing a role in contributing to, things like ranking or school performance. So those are some examples. And then, you usually have the larger population. Level 2 is the group user item. Level 3 is the individual ratings. So, okay. And then kind of similar to the example that I was giving with, you kind of want to be somewhere in the middle. This is also going with hierarchical modeling. We have the concept of partial pooling. So we want a combination of where it's not just solely the global level, which might be like a large entity, like a school or city or country. And then, we want to also take a look at individuals as well too. So partial pooling balances those two. So independently, which is no pooling, and then combining them, complete pooling would be looking at the larger level, and then individual would be more like not so much of pooling them. So partial pooling is like right in between. You want the global, you want to take at the larger level like a school, but then you also want to factor in individual performance. So that is partial pooling. So we have like different concepts like shrinkage, which is, it helps reduce that variance, especially when you have extreme estimates in a small sample size. So maybe you're taking a look at 5, 10 users and their ratings. Some of their ratings might be on one extreme to another. So shrinkage helps with that. It also helps overcoming problems of overfitting, for instance, or underfitting. So, making sure that the different tiers are defined and leveled. And then, yes, hierarchy is, again, the relationship between them, like what I've showed here. So we've got the top, bottom. And then, just to put them all together, we have hierarchical modeling and Bayesian stats. So I know I'm introducing like a few new things, which can be a lot. So just to break them down as to what each component might be doing is you have multi-behavior modeling. So it helps connect maybe in a specific population, like it says here, clicks, likes, or purchases, maybe like a specific demographic of users. It can be taking a look at like their occupation or personal information, like where they might be living, or gender, race, things like that. And then maybe connected to like an individual as to, are they fitting in that majority, or are they deviating a little? We also have attention networks, explicit and implicit hierarchies. So some hierarchies that aren't really defined as well as others. So that's a little bit of hierarchical modeling. We also have incorporating Bayesian stats into that. So again, it will help resolve some of those problems that we have, which include sparse data. So priors coming from broader categories or, information that we don't have enough for users or new items entering the system. Cold start problem, and then scalability as well too. I'll talk a little bit about the inference methods as well too, because the one that I have on the notebook will work well with a smaller data sample, but it won't necessarily work if you have a lot of data. So that's where like variational inference algorithms would work better. Okay. So just to visualize the concept a little bit more, we've got no pooling, partial pooling, and complete pooling. So you've got the individual parameters for no pooling, partial pooling is right in between, and then complete pooling is including the whole group. So all right. Now comes, I guess, the fun part. So this is PyMC. It's a probabilistic programming library for Python. It's one of the main ones. Like I know there's been different iterations coming about. So if you happen to know them, do feel free to let me know. I'm also relatively learning as I go, as I'm sure all of you are. It's used for Bayesian statistical modeling and probabilistic machine learning. And then it uses the Markov chain, Monte Carlo, and variational inference too. So that's just a little bit snippet of what the model looks like. So I know I kind of already went over a little bit of the layout of the model. So now I'll go into combining it with the hierarchical structure. So the previous model that I showed you was just for all users and items, but obviously in the real world, you're going to have users behaving differently and interacting with the items differently too. So it's just to see, in this case, you'll see that the root mean squared error doesn't have much of a difference. Maybe it might be the case with how the data set is, but if you're looking at things that have some sort of level or hierarchy, I think that would be really beneficial in taking a look at it. So I just sample users so that again, it wouldn't take too much compute time to run all of that. So training the users, we get the train sample, and then we get the.
I have a question. I'm running the previous cell, the cell that's before the part 4B.
Yes.
It's been, I guess, 8 minutes. Do you have an estimate? Is it long? No.
Yeah, I don't think it should be that long. I made sure. Yeah. Is it a specific
BMF model? Raise BMF.
Oh, okay. Oh, is it the BMF model? Oh, yeah. That one will take time because there's like a lot more. Because you have the K in, and then you also have the user and items, and then you multiply that with the K, so you're gonna have like 19,000 with that.
Excuse me. Just a quick question, is there a shortcut for reevaluating online while somebody's shopping, reevaluating those statistics, or do you have to go back and recompute the whole thing again?
Yeah, I mean, I guess that's where like a lot of this modern day like LLMs and agentic AI, I feel like that's where a lot of those opportunities would come and save some of that time. So
there's no shortcut built into one of these techniques that you could just like joint priors for the prediction.
Yeah, at least not that I'm aware of. That's something that I haven't done too much research on, but I know, again, that's where at least from what I'm gathering, I think that's where that could be a good opportunity for the LLMs and agentic environments to explore. So, because with some of the data sets that I've been working with, there's been other problems that I've been focusing on, especially when you're dealing with the actual text itself, like the ratings. That was I was definitely more focused on, that might come in handy. What is the way that, when you have these new users and items entering the space, what are some ways we can pre-process, all of that information? That would also be a good next step too. What are some opportunities in that space for sure? Sorry, I was like, I wish I had a better answer, but
No, that's
Yeah.
fair. Thank you.
yeah, no worries. So, and then let me just see where I left off of. Okay, so yeah, you do the label encoding. That's just the way how PyMC reads the data. So you'll need to do that for your users and items. This is like the same code that I used for the Bayesian matrix factorization. I'm just bringing it down here again, just for consistency. So known users and items, these are the users and items, like they are rating it and the users are actively rating them. And then you split them into a test data set with user and item ID. And then you, again, do the same thing, users and items, unique numbers on those. So just to put into context as to, we're looking at 500 users because that's the number I decided to train on. We've got 1429 items, like movies, train, test. The ratings will stay in that range between 1 to 5. The rating mean is 3.5. Standard deviation is 1.131. So you see here that the rating mean is slightly higher than 3.5. So, I could have gone maybe like 3.52 to be exact, but sometimes when you see the graph, you might think, oh, maybe it's better to eyeball it lower than higher. So, and then this is the formula, kind of similar to the other formula that I showed. So I have the global mean, I have the user offset. So I'll explain in a little bit what that means. Item offset as well. So global mean is the overall average of ratings for the data set. The user offset is for the individual users. So that's one value per user. Are they rating above or below the global mean? And then item is one value per item. So how much it gets rated above or below the average. And then, they share a common prior because we are doing partial pooling. So we're trying to combine both of that structures. But again, in this case, hierarchical modeling might not be the best case because we don't have that much information on the users themselves. Maybe when we get the data, and maybe it will tell us something different. But so you define the model. We're using half normal priors on the user and item, and then we have the global mean. Then we have the user offset, item offset. And then the shape is based on the number of users and items. And then we put it all in the equation together. So you'll have the global mean plus the user offset plus the item offset. And then we have the sigma observation also at half normal. And then we'll put it together getting the rating observation. So that will take a normal distribution. Mu is expected, so we defined that earlier with the global mean, user, and item, and then sigma is above defined, and then observed is the, trained sample rating. So that's the data that we're using, and then just to visualize what the hierarchical modeling looks like. You're able to also do that using the PyMC package. So that's nice if you want an extra evaluation. So, sorry, I didn't see it.
No, you're good. I'm still trying to understand the hierarchical structure. Like, so on level 1, we got ratings. Then level 2, we have users and items.
Yeah, I think in this case, it would be like all of the users and then the individual users. So that's why I said for this hierarchical modeling, it might not be that great to be applied here, but maybe if you were taking a look at maybe the users are grouped by like high school grade or something, that's when it would be helpful.
Okay.
Yeah. Because I realized, I think the data set that I picked was the best use case for that. But if there's like, there's like a specific data column as to maybe their location or country or occupation or something like that, that's when it would be beneficial. Yeah, but for this case, that's why I was like, sorry, I should have made that clear here. Like, it's not the best example, but maybe when you get the data and you see that, like, maybe this slightly performs better, maybe that will tell you something like, oh, maybe the users maybe there's some sort of hierarchy going on, but we don't know too much because unfortunately, the only columns with this data set is user, item, rating, and the time that they rated in. Yep. Anything else? Yeah, after when I give the tutorial, like I'll go through, some of the links and resources, because there's a lot of data sets that you can try this on. So I'm sure that they'll have better columns defined if you're interested in seeing some sort of hierarchy or organization there. Cool. Okay. So yeah, have the likelihood defined. So in this case, I have total of 800 draws. So 300 of them are, kind of used for tuning purposes, and then 500 of them are actually, being drawn. Did it twice. So I did 2 chains, and then target accept, return inference data, and then the progress bar is this one below. And then you're able to save your checkpoints locally as well if you need to come back and refer to them again. So that's what the likelihood looks like. And then, more interpretation of different metrics. So we have R hat, ESS. So I just wanted to show that you're able to get for your global mean, for user, item, and observation, you're able to get standard deviation, and then, what are the 3% and 97%, like what intervals, what's the lower and upper bound that they fall under. And then, I'll go over the other ESS and R hat. So the R hat, which is the conversion, it's usually nice to be around 1, but sometimes you'll get it slightly higher than 1, depending on convergence issues. And then also, again, depending on how the data set is. The ESS stands for effective sample size. So usually if that is greater than 100, that is good to have. And it's also like how much independent information that we have. So that means like it's just like showing stability and convergence. So usually when we print out the summary metrics, you would do like az.summary, the trace, and then whatever variables you want to see. That will give sort of an instance as to, is the model performing well? Are there instances where there might be some, values of concern, like maybe is the mean not in the range, or is the R hat, higher or lower? Same thing with the ESS. So let me just see here. So when I ran the code, maybe if you run the code on your end too, you'll see that it will say, oh, you have a low ESS. And this is what this means is that the global mean is strongly correlated with the user item offset. So in this case, because we don't really have a clear hierarchy structure here, I think that's why it gave that warning. So nothing is wrong with the results. It just says that, like, this might be the reasoning. Like, hey, just a heads up, you have that warning on there. And then, you're able to visualize your plots. So we have the global mean for the user and item. And then let me just show really quickly as to the interpretations. So the left plots show the posterior distribution. So remember, the posterior is what you get after you combine the prior and likelihood, and then you do the the running that I've showed you, and it should look unimodal. So you can see that based on these charts that, relatively the posterior is within the range. And then the right plots, these are just the sampling traces across iterations. So remember, we had about 500, like we had 800 total, but then 300 of those were, used for like trading purposes. So that's just showing what happens at each and every step for your item, user, and your global mean. So you can kind of see here something might have happened. I don't know, kind of in the middle. But overall, user and item look all right for the most part. So you can see kind of some differences. I know it's kind of hard to tell the light. Yeah. So yeah, these are yeah, so these are all just ways to kind of assess and evaluate how well your model is doing. So you have summary, you can run plots. You can also calculate metrics, what I've mentioned, like RMSC and understanding the recommendation quality, all sorts of things. And then wanted to bring it back to our baseline model as to, why using Bayesian methods might be the better way to go. So I have here the posterior and then the one for the user and the item. So you can see the distribution here, like it's fairly normal for the most part. Kind of all centered in the middle. And then, yeah, these are just this was just me checking some of those things. So getting the count, mean for users and items. And then, yeah, you're able to run the RMSC for your hierarchical model. And then you can like kind of compare to see performance wise, obviously there's not much of a difference in this case because I just wanted to show how Bayesian stats is applied in probabilistic modeling. So what I've worked with a lot is with hierarchical modeling. So that's why I stuck with that. But yeah, I mean, again, you can do like Bayesian matrix factorization. I have that on there, like I mentioned, but yeah, I didn't want to spend the whole session trying to run that because it would be very long. So yeah, that's why I just wanted to show that, like, yeah, again, depending on the data, the hierarchical could work, but because in our case, we didn't have like a clear order defined, that's why it's like, it performs a little bit better, but still kind of relatively the same. Okay, let me just see if this is the one. Yeah, so this is ratings between a dense or sparse user. So this might be someone who is giving a lot of ratings, whereas someone else who's only given 12 ratings. So going back to the earlier example that I showed, let me just go back to the presentation. I said user A for the baseline recommender systems model, that rating was at 4.53. User B just gave 12 ratings. Their recommendation on average is at 5.51. But then after incorporating that probabilistic framework and also the hierarchical structure, this is what we get based on what we've done. So yeah, you can kind of think of it like those might be prior values. And then this is what we get after when we get the data and we update it accordingly based on the prior belief and then the data that we get. So our actual mean is at 3.44 for someone who's given a lot of ratings, and then someone who's given like not so much ratings, like 12 ratings, rather than 5.51, their rating might fall under 4.09. So yeah, that's kind of like an application as to, how this might be beneficial, especially when you have instances where you might question yourself, like, oh, are these the right numbers based on running like the baseline models? So that's what you get after doing all the calculations. Wow. Yep. And then, yeah, this is the evaluation and results. Yeah, this was, again, I've calculated this several times, so sorry if the numbers are a little bit different, but yeah. You can see here with the sparse user, like it's a total different number. Like, you have it at 5.51, but it ends up being at 4.2. Whereas the dense user, like, there is a difference, but not as much. So just wanted to show there, how this might be beneficial. And then, yeah, this is for the Bayesian matrix factorization. This one's an error because, yeah, it took some time to run the model. So that's why I can't run that code. But yeah, just kind of wanted to summarize everything. And then maybe I'll show some of the links that you can all check out. And then, yeah, feel free to comment or ask any questions. So yeah, with the baseline models, it tends to treat all users and items equally. So you might not necessarily know, like, okay, if two users give the same rating, then it will just assume that, okay, overall this movie is a 5 or a 4. It doesn't really account for data sparsity. Sorry, did you have a question? Okay. No, okay, I just wanted to make sure. Okay. And then, yeah, so again, sparse users produce unreliable estimates. Dense users who have many ratings, they tend to give a more accurate picture on their rating because they'll have a lot more ratings, right? And then we have hierarchical Bayesian solutions. So you've got the partial pooling model, which factors in the global. So everyone in your data, and then maybe what specific maybe individual that you're taking a look at or categories. And then, yeah. And this is the model structure. So global mean, user offset, item offset, and then why this matters, reduces overfitting of the model, helps improve stability. Like, what I've showed you, even with that small subset, the model overall stabilizes and converges well. And then also just trying to provide uncertainty aware estimates. And then let me see. Yeah. So usually, for the most part, hierarchical Bayesian models tend to do really well with simple baseline models. Yeah, especially when you have some sort of structure in the data. So yeah, again, like whatever data set you might be working with is key to knowing, like, which model to use. But overall, the probabilistic framework really helps address some of the problems that you might run into in the recommender system space. You'll have new users entering in the system, or sparse users, like maybe trying to fill up that matrix that I showed you earlier, or even trying to reduce, some of the predictions that you get, like really question, are those accurate or not? So it helps it right there. So yeah, that was pretty much all the like coding knowledge stuff that I have. Just wanted to open the floor for any questions or comments. Yeah, go for it.
Is there a risk that the underlying distribution, which you assume to be model, is going to get increasingly left skewed as like more ratings? And so, is there a way to dynamically change that? Or
Yeah, no. I mean, that would be like a good thing to have. Yeah, especially if you have like new users or data entering the system. Yeah, I think I don't know off the top of my head, but with the one of the distributions that I mentioned, yeah, I think you would just maybe define that beforehand, because I remember even learning there are some other distribution types that do account for, maybe you have like two, like sorry, I can't think of the word, but you might have like two extremes in a graph. So there's like some distributions that do a better job accounting for that, rather than normal. So yeah, I mean, for me, I've defined it beforehand, but dynamically, yeah, that might kind of do a similar question, maybe more of an agentic, yeah, way. But yeah, when I've dealt with it, usually I just try to, pick that different distribution and then go off from there. So yeah. Anything? Oh yeah.
So you mentioned before, like the BMF model will take a much longer time to calculate. In a production environment, when would you be running those calculations? While the user's offline, or when would the process? So
Yeah. No, that's a good question.
daily calculation for all of your users, or so logs off. Now we can recalculate because they're probably not going to log back on anytime soon.
Yeah. No, yeah, I guess it would depend on like how in that sort of environment, how you would define it as. Like, I know when I've worked in some of those situations, it would maybe be like, you schedule it at a certain time, it will make that update at like, midnight at this time or 1 p.m. at this time. So yeah, I guess it would depend on the situation on like how often you want to be updating it, or you know what time, and yeah, the frequency of it. So yeah, I guess it would be like a situation dependent question, but there are ways to do it so that it doesn't get too overhead with compute time and resources. Okay, anything else? Yeah.
Have you thought of using like the genre for example, like movies?
Yeah.
To kind of like incorporate that hierarchical structure, so it might make more like something like that.
Actually, yeah, no, that would be a good point. Yeah, maybe that's like something, maybe like an interesting analysis to do that. Even I myself have been trying to do is, try to incorporate clustering with these hierarchical models. So yeah, maybe that's one way you can tell like, okay, why some of these data points, might be clustered. It might be because of a genre. So yeah, maybe that would make some things better and tell a better story as to, maybe what gets more, why something might get more ratings than another, like what user preference might be. So
Yeah, could you talk a little bit more about that clustering approach that may be a little too technical for us right now, but like instead of having a hierarchical establishment of these, what if they're just some sort of cluster according to some uh, dimensionality?
yeah, no, actually that's like one of the sections that my thesis actually focused on, was like pitching this model of clustering. So like I'm definitely on the weeds and depth of it, because what I pitched was having this hierarchical structure, but then having this like mixture model component that will have like a cluster that will like put the users into one thing, because there's not been much work done on incorporating that work into like a basic regression. So yeah, right now what I've been trying to do is like, yeah, like that I've just been on the methods part right now, just making sure that everything's well defined and right. But yeah, that's like one way to kind of see as to, like how, like what patterns we can get from the data, right? Like, they're like active users, or are they like tending to over or underrate? Maybe like I was looking at a recipe data set. So, maybe some things would be taking a look at, like, obviously we couldn't tell specifically because, everything is all coded and stuff. Like maybe are there specific, recipes that people tend to like, have more representation in, because there was also like a category for recipe types. So, the clustering might be helpful there. But yeah, I mean, I myself have been interested in that because it gives sort of a pattern as to, what the, again, because I mentioned like users and humans are so complex. So like it might give us a sense as to, where their preferences might be, and, give some sort of like understanding. Like I'm combining like different things like the hierarchical structure and this. So that's why I'm like, it might be telling a little too much of a story that's not intended to, but it's like really helpful to see as to, maybe what sort of things are going on. Sorry, I haven't like got back in. I'm supposed to be doing some work on it. So I'm like, this is good way for me to get back into it. So sorry if it was all over the place, but these are just some of the thoughts that I've been having while I was working on that. So yeah, go ahead. Mhm.
So the risk of like overshooting past the max rating or the min rating, is that something that's entirely eliminated by this approach?
Yeah, so what it would do is it will consider some of those users who, might have not given much ratings, or, given little ratings. So for a hierarchical model, it might use the global mean to define that sort of direction. And then even without the hierarchical structure, it will just give like a general baseline as to those users, like, that might have not left much reviews, or who were outliers in some instances. So to try to normalize some of those cases, because if you look at the baseline model, like, yeah, they either don't factor them in, or yeah, like it doesn't provide like a full context. Yeah. So that's what like the prior distribution helps with that. Or pretty priors on them, yeah. Cool. Anything else? Yeah, hopefully this was helpful. Like even if you don't do a lot of work on recommender systems, but at least using that package might be beneficial down the road, especially if you come across it. So yeah, still got a few minutes left, so I'll just click on some of the links just to show you what are some things that you can do. So this is the PyMC page. So yeah, one key thing that I just wanted to quickly mention is, yeah, the Markov chain Monte Carlo uses like the no U-turn sampling. So it doesn't really work well with large data sets. So with the earlier question that was being asked, like you were asking about like users, like, getting a whole bunch of, like their user data in, like you would probably want to go with a variational inference, just because you'll have like a lot more data and, that might be better in the real time setting. Yeah, very user friendly, like that. So they have like an example data set. And then, yeah, this was some of the things that we took a look at. So yeah, there's even like visuals, like an API that you can use there. And then this one, I didn't go over the libraries in depth, but this one is the Bayesian visualization model. So all those plots that I was showing you with the posterior, this is the model, this is the package that uses all of that. And then, yeah, this is the data set. And then there's like a whole bunch of other data sets that you can use here. And then, yeah, I'll just show this really quickly because this is where I pulled a lot of the data sets from. So yeah, if you're interested, there's like a lot of different data sets from the UCSD page. So they've got data from like Amazon, Pinterest, Facebook, Twitter, Google Plus, even Reddit. And then if you're interested in like, I'm curious to see, even there's been some work done on multimodal recommender systems, but there's not been as much. So yeah, like you see here, like, you can even get some images to like some of these data sets have images. So yeah, it'd be kind of interesting to see, if you combine different modes of data, like how that might play a role in the same review data. So yeah, you're able to see that. The nice part about this link is it tells you, maybe if you're interested in that hierarchy structure, like maybe taking a look at, what are the variables that the different data sets use. And then, like we pick the data set accordingly. And then, yeah, the other couple links are some books and further reading, but yeah, that is, I think, all I've got. So I was like, hopefully I can give 20 minutes back to your schedules before the next session. But yeah, I mean, feel free to play around with the notebook, or also like if you have any questions or suggestions or even ideas, like happy to listen to that.